video is about the bias-variance trade-off and the difference in performance between training and test set. So we are given part of a population and would like to estimate the mean of the population. Consider the simplest data sets. We have only two examples, 1 and 2. This is the whole population and the mean is 1.5. We start the experiment, so we get training data sets. We draw only one time. This is the first training data set. It's a sample of the population. And our model for the average is the average in the training data set is the average in the population. So we can throw 1 or 2 possible data sets with 50% probability. Our prediction according to the model for the average in the population is 1 and 2 respectively. Now we would like to test out of sample the performance of the model. For the first case in training set 1, we have prediction 1 for the average and the test set is 1, 2, 1, 2, 1, 2, etc. So this is the whole population. Training set 2, our prediction is 2. The error is 0.5 expected one on training set 1 and 0.5 is training set 2. So we don't know which training set we have in the beginning, so our expectation is the average of these, which is again 0.5. The expectation of the expected prediction squared error. We can decompose it into base error, mean, expected mean square error, which is base error plus the bias square plus the variance. Note that the expected prediction is a half of 1 and a half of 2, which is 1.5, which is exactly the same as the population mean, which means that our estimator isn't biased for the mean. We end up with 0.5 expected prediction error. Now consider another model. We start with exactly the same setting, and the model is our prediction for the average is 0.9 times the average in the training set. We have exactly the same situation, training set 1, training set 2. Our prediction from training set 1 is 0.9 for the average and 0.8 for the average from training set 2. We test out of sample again. We have our constant prediction. Test samples come one by one in the test set, and then we have a squared error between the prediction for the average and the test example. And from training set 1 we have that the expected prediction error is 0.61, and from training set 2 it is 0.34. On average 0.475, which is less than 0.5. Let's decompose again the expectation of the expected prediction error. Note that the expected prediction for the mean is 1.35, which is different from 1.5. So the estimator is biased, and the bias squared is 0.0225. But the variance is smaller because difference between 1 and 2 predictions is bigger than difference between 0.9 and 1.8. So the variance of the prediction is smaller. Bias increases, variance decreases. As an end result, the expected prediction error decreases. So even if our coefficient before the average of the training set, this penalization term, is between 0.8 and 1, we get expected prediction error less than 0.5. But the optimal was 0.9. How did we find this penalization? So let's see. In general, we have two training sets and we have two estimates for the mean by applying a model. And we have expected prediction error from model 1, expected prediction error from model 2. Let's consider unbiased estimator. So that the expectation of the prediction for mu is equal to mu, like the model 1. This is unbiased estimator, model 1. Let's see if we add alpha times prediction if 1 will be optimal, or 0.9, or any other number. We take the derivative with respect to alpha of the expectation of the expected prediction error, and after some calculation we can see what alpha should be equal to. Here, because we have constants, we can get rid of the expectation over training sets. So alpha is equal to mu squared divided by mu squared times variance. First of all, it's positive. Second of all, it's between 0 and 1. And by the way, to compute it, we need to know the real mean. So we can never compute it, only in theory. The way to get it in practice is via cross-validation. So the difference between training and test performance. The expectation of the prediction error for a model 1, the unbiased one, was 0.5. So if we decompose expected prediction error, we can see that there are actually three terms. There is expected mean square error, base error, and covariance between mu hat and y. So between the test examples and mu hat. Normally it is 0 because y are test examples and mu hat is from the training set. However, if y is from the training set, then there is covariance. In this case, mu hat is equal to y, because y from the training set is 1, mu hat is 1, y is 2, mu hat is 2. And we get that the performance on the training set is 0, the error is 0. However, on the test set it is 0.5. So the difference between training and test set is exactly 2 times covariance of mu hat and y. In the derivation, the covariance term was not exactly derived, so here I show how to derive it in practice.